The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So who has a question? What chapter did we read?
The common sense chapter?
Yes. People are always asking me what common sense is, and I try to explain that there's no such thing, but it's relative, namely, you're always in the context of some social group or other, and common sense is the collection of knowledge that you assume other people know, so that, and of course there's some things that everybody knows, like elementary physics. If you release something, it falls. And if you tell somebody that, they'll think there's something wrong with you. Because why are you telling them things that they don't know, that they already know, and that presumably you know that they know, and so forth. So, what problems did you? Yes?
So I have a question. You talk about building a baby machine, right?
Yes.
And then you kind of get into some of the problems of building a baby machine and kind of how it's an issue of maybe it's tricky to get it to represent data in a meaningful way. And so what I'm wondering is, with real babies, we have lots and lots and lots of reinforcement within primates, what we were talking about earlier on in the class. And so I'm wondering, if you did have something like a baby machine, lots of reinforcement on the baby machine, telling it, not only what's right and wrong, but, and is it thinking about things in the right way? Couldn't that potentially lead to a better baby machine?
Well, people have tried to make machines that are based on reinforcement, but what is it that you're reinforcing?
Well, right, so I mean, not just reinforcing the action and the result, but
Yeah.
maybe also reinforcing how it's thinking about the action.
Yes, if you could see that's really what the critic selector model is supposed to do. I don't think I talked about, I probably should have had a little section in the book about how one develops critics, but in fact, I was noticing that there wasn't any place that I said that a critic may use a whole way to think to work. So maybe the book looks too simplistic, but there's a real trouble with reinforcement, and I think you put your finger on it. Namely, you don't reinforce the external behavior, which is all the parent can do. But what you want is the machine to reinforce the process that got a good result. And I think somewhere in the book, I quote Alan Newell, who pointed this out a long time ago, like in the 1960s, that for example, in a chess program, if you want a chess program to learn, it's no use learning from its, suppose that the machine managed to win a game, then if you take the old principles before cognitive psychology, what you do is you reinforce the last move, namely the one that produced the checkmate. But that won't get you anywhere, except that after 1,000,000 years, you might reinforce a lot of ways to get to the checkmate. But what Newell says is if you're going to make a chess machine learn, it's going to have to do some kind of credit assignment and reinforce the strategy that got you into the winning position. So I'm not throwing away the idea of reinforcement. It's just that for almost 100 years, psychologists tried to make theories of rewarding the machine for success. And dozens of people have started, I don't know if it's dozens, have tried to make baby machines. There's a guy named Ben Goertzel who talks about a project to make a machine that will start with almost nothing and learn. And I suspect Jeff Hawkins sort of is talking about making such a machine. And over the years, various people have not only proposed such machines, but fooled venture capitalists into starting companies to develop them, and they all flattened out. Maybe the first interesting machine that started with very little was Douglas Lennett's PhD thesis, which was called Automated Mathematician, and another project that he did after that called Eurisco, which learned from experience. And both of them flattened out after a while. That is, they very rapidly learned some interesting things, and then it became minutes or hours for them to learn another interesting thing, and eventually days. So all the baby machines have, that I've heard of, have flattened out and not got very far. So I think I suspect that what's happened in human evolution is that, one question is, how could such a machine invent a new representation for some new kind of problem? And I suspect that our brains come with genetic provisions for making things like semantic networks and scripts and certainly things like transframes. And when you have a transframe at a higher level, it can say, if you're thinking this way, then, or if the problem is of this kind, then I used this strategy and that worked really well, or I used that strategy and it didn't, and that way you develop critic-selector pairs. But I don't think that any baby machine that doesn't have provisions for this kind of multi-level activity would spontaneously develop them in less than very large numbers of trials, like 10 to the 15th or 20th. In fact, we have 10 to the 20th ancestors, if you go back to the first animals. And so we got this evolution. It was very massive. And if you take the evolution of mammals, there must have been 10 to the 15th mammals by now. Now, most of them aren't our direct ancestors, but there's a thing called lateral transfer of genes. And no one knows how important it is, but I suspect that here you have birds, and here you have people, and maybe at some point in our ancestry when birds and mammals weren't so far apart, they both had somewhat similar brains. They came from some common vertebrate ancestor, namely the dinosaurs. We're a kind of bird, some people believe, but not a flying bird, but a bird that still had hands and was a frisky little mammal. And one theory is that every now and then there's some kind of virus that here this strain of birds developed some interesting brain structure, which is genetically controlled by a few genes. And this bird ancestor gets infected by a virus, and like the Asian bird flu, some little mammal catches that virus, and in the unlikely case that the virus infects a germ cell, you might get a new gene. See what I'm saying? Once in a very long time, your species can inherit a gene from an unrelated species. So that means that the gene pool is enormous. And if this happens every million years on the whole planet, then It's 100 million years since the mammals appeared, and so we could have caught 100 of these brain genes from some relatives. So lateral transfer of a whole intact gene by a virus or something is presumably it's very, very rare, but there is evidence for some of these. Some animals have identical genes to other animals that are not related to them by, that are pretty far away. And this ability to catch useful genes from other species means that in the rare event that it happens, you're getting hundreds of millions of years of evolution for that structure. Now, most of those genes won't do anything because they won't come along with the right stuff to activate them. But my point is that evolution has a larger scale than most people are told, because how many of you have heard of this lateral transfer of genetic material? It happens all the time in bacteria. That is, every few minutes in a petri dish. So there it's generally understood that bacteria can catch these little, what are they called? They have circular chromosomes, and sometimes a little loop splits off and another bacterium eats this one, and its genetic stuff gets incorporated. So if you get a bacteria that's resistant to some antibiotic, all of a sudden, other unrelated bacteria can acquire that resistance, because antibiotic resistance is often carried by a single gene. It's some gene that makes something that inactivates the antibiotic or whatever. That's a long story, but people are still proposing baby machines, and they're hoping that they don't have to have something like the genetically organized 6-level structure of differentiated kinds of processes that the emotion machine book proposes. In fact, we're looking for some philanthropists to support programming more of that, and it's a big job. And Push Singh PhD thesis is the first attempt to make some of that structure. He did about 3 levels of it and made large numbers of arbitrary decisions, because when you're writing a program, you have to make something work. And it's going to take a lot of high-level thinking about the architecture before we try to program anything much larger. But I hope in the next few years we'll get support to do that. Anybody who wants to help can help, but right now we don't have funding to hire you. It's terribly tempting to try to make a baby machine. There's one theory, the theory of algorithmic probability, which some people think, some people think if you just collect Bayesian statistics enough, you can make a machine to solve any kind of problem. But you need to be very smart to decide you need credit assignment to make a Bayesian statistics machine get better and better at some point. There are lots of them that work pretty well on certain problems, and then as far as I know, they flatten out, and it takes longer and longer for them to invent a new category, because you need some credit assignment-like process to decide which all probabilities are conditional on things in the state of the current environment, and to make a Bayesian network that efficiently figures out which new factors might be relevant might require some real thinking rather than just collecting statistics blindly. Conditional probability machines, in principle, could eventually learn anything, but they don't look practical to me anyway. There's this theory of algorithmic probability, which was developed by Ray Solomonoff, who lives in Cambridge, and the Russian mathematician Kolmogorov when he was investigating the foundations of probability, and also Gregory Chaitin at IBM made some contributions to that. And that suggests a kind of machine that sort of collects sequences of operations that have been significant and makes combinations and sort of considers all possible programs of a certain length and figures out which of them succeed most often. So in principle, that's another theory which could be a baby machine that eventually learns enough to be smart. But that's a very beautiful mathematical theory, but it's sort of uncomputable. What you have to do is look at what all possible Turing machines of a certain complexity will do and see which of them solve the most problems in some set. And then the theory suggests how to make, how to extend these as you add more problems. But nobody's found a practical approximation. The algorithmic probability involves looking at all possible Turing machines and weighting them by their complexity and using that to decide which machine to apply to solve which problem. It's a very elegant theory, but you have to look at all possible machines to get these numbers, and if you look at a finite number of machines, then you get an approximation to it. And a few mathematicians have tried to think of practical heuristics to make these things work. I don't know of any that ever passed, ever learned much. But the baby machine appeals to investors because it's so easy to say, we'll just reward it when it succeeds and it'll get better and better.
But there are still scripts inside humans, procedural scripts that come with a baby to do things like, a baby bird, it will be building, like in a bird it will be building a nest, or in a horse it will be running or something like that.
It's a nice question. Are those scripts or what? But lots of animals. Just consider a beaver. It chops these trees down and drags them over to the right place in the river, and I suppose you don't need a script if you have a lot of if-thens that are just right. If you see this situation, do that. And then you have a sort of superscript which turns on some block of these when you're in the neighborhood of a tree and you're in a state that you're building a dam.
Or something that results in a script.
Incidentally, the animal where the scripts are best understood are spiders. Spiders are easy to breed and keep in the laboratory. I don't believe anyone's ever raised a beaver that successfully built a dam. But in spiders, they know a lot of genes, and if you knock out a certain gene, the spider will build the web just so far, and it won't make the second. In a typical orb spider web, they make 3 or 4, I think 3 lines coming out from a center, and then they make a very coarse spiral. And then they weave a very fine spiral in between these and eat the coarse one, and so on. And there's a lot of steps are known in this script, like how they swing the initial fiber over and run down it and make another one that goes down, and I forget what happens then. And they've been able to knock out genes so that these things will get up to a certain point and then stop. And then if you take that spider in a net, drop it into a web, where another spider has got past that stage, then your gene-deleted spider can finish it. But it isn't clear that these are in a script. No one knows very much about how these processes are activated at each step. And they could be just if-thens. If the web looks like this, do that. But I don't know.
I was trying to make kind of a distinction between the words that I was using. It was linguistic versus sublinguistic scripts. So,
Well, birds learn songs, and that looks like a really clearly wired-in script of some sort. But I didn't mean to interrupt.
yeah, well, what I was saying is that scripts that are linguistic versus scripts that are sublinguistic. So linguistic scripts would be that you can modify and debug.
Mm-hmm.
And represent the debugging and all that in words themselves. And some of the sublinguistic scripts would be still procedural, but things that you're not being debug, or
Well,
maybe memory retrieval scripts or some low-level.
yeah, when Deb Roy collects all of the things that this infant has said for 3 or 4 years, then you might be able to mine it to see that the child said something on one occasion, and a little later there's a different version which is an edited version of the first, maybe a huge data bank of everything that a child ever said would make it, would be a good database for making theories about that.
The main reason why I said that, because I was trying to understand how to implement ways of thinking. And if you try to algorithmically define a significant way of thinking, like making an analogy or dividing and conquering and things like that, then it's much better represented using English or some of the terms, some of the typical terms that we use.
Using sequences of symbols that you can manipulate. It doesn't have to be language, but that is, deaf people are pretty smart, even if they're not taught a language. But
what I really mean is all the things that we have in language, like analogy or semantic hierarchies, things that allow us to make generalizations, a bit of grammar and things like that. It makes it easier. It makes it much more expressive to write programs or write scripts of large-scale thinking activities in English than to program them using restricted language
like if-thens, like productions or if-thens. Yeah, I'm sure that the difference between humans and most other animals is not necessarily language, but the ability to manipulate strings or little trees of symbols. And at some point you say, this worked pretty well, I'm going to make a copy, but I'll reverse these two. A typical bug in Gerald Sussman's 1972 thesis is you have a couple of you have a problem, you split it into some sub-goals, then you try them in a certain order and it doesn't work because your first action has changed the condition so that the second one doesn't apply. And a good heuristic is, that example came up when we were trying to make a robot build stacks of blocks, stuff like that. And suppose you wanted to build this. So you say, well, there's a bottle on top of one brick, and that brick is on top of another, so let's achieve this. By the way, our robot had only one hand. I forgot to mention that. So now you're stuck because now you want to put this brick on that and you can't lift it. But it would have been better if you said, well, let's do this first and then that. And Jerry Sussman's thesis has about 10 common bugs in procedures and various ways to change your goal structure to achieve it. And that was 1972, and I've never seen another thesis on bugs. Anybody run across one? Did you ever? I annoy my colleagues by continually referring to Sussman's thesis and Patrick Winston's thesis, which did all sorts of sensible, commonsensical things. And then there's this army of AI researchers who try to make Bayesian nets work or genetic algorithms work or whatever. And none of them include the process of dividing a problem into several parts and trying to solve them separately and overcoming the bugs like that happen if you don't get them in the right order or don't satisfy the right constraints. So I keep complaining that very little has happened at very high levels in a long time. Now, what has happened is that the methods for doing Bayesian induction have improved greatly, and they're industrially very useful for various kinds of problems. But nobody knows what kinds of problems they're good for. They just know some examples. And neural nets are very good for making voice recognition slightly better, and so forth. So these are mature fields, but there doesn't seem to be any place for researchers to do things on a higher level and debug higher level kinds of common sense reasoning.
Actually, I wonder if people have even written papers on debugging common sense knowledge databases, just procedural scripts to identify bugs in chains of reasoning and just activate them and use them if there's a problem there.
Well, there are a lot of books on system programming, and I've never read one of them from end to end. And maybe there's somewhere there are probably 100 books on how to write programs. And maybe each of them has a few paragraphs on A, how to plan ahead so you don't have any bugs, or B, how you fix bugs. And it would be nice if there were a way to collect those paragraphs and see if there's some community wisdom, but the natural language search engines aren't good enough to find those, I think. In Jerry Sussman or Richard Stallman or somebody like that, in those persons' brains, there's a great deal of knowledge that the rest of us don't have. And, there should be some way to take their PhD thesis away and make them write another one. Speaking of birds, in the 1990s, it was discovered that in some birds that learn songs, like canaries, the part of the brain that contains the scripts for the song atrophies and dies every spring, and a new bunch of brain tissue appears in that same canary, and it learns the song over again from its friends. So there's a peculiar case in which brain tissue continues to get replaced every year. Birds live quite a long time, too. And
So is the song ever forgotten?
the song is forgotten if its friends aren't. If you take the bird, if the bird doesn't have anybody to copy. I don't know that that's a good fact to know, because it's nobody has found anything like that in any other animal yet.
Do the songs change?
What?
Do the songs change?
The songs change over the years, yeah. But they're very specific, and if you sing the wrong song, the bird will bite you or run away or something.
Maybe
Yeah.
sorry.
Yeah.
Maybe the spider that's missing the gene that goes and joins the other spider and finishes the web. Maybe if it got there a little earlier, it could learn whatever it lacked due to the missing gene.
It's not clear that they can learn it, but once they know more details, they might be able to insert new genes so that it makes better webs. I don't know. It's interesting that biology is like other things, and you get whole communities that get interested in one particular animal or one aspect of an animal because it's easy to observe or something. And I doubt that anybody knows as much about any other insect. I don't mean insect. A spider isn't an insect, is it? It's an arthropod or something. That's just a name.
So, Marvin, if you talk about that the baby machines are not succeeding, so what about the learning machines? Are we able to construct machines that learn?
There are machines that learn the statistical machines and the neural network machines learn various things, but they flatten out. And I don't know of any case where any of them have learned higher level strategies. This is Jose Valenti, who was a PhD here when? 83. And I could tell a long story about him, but in the 60s and 70s and 80s, it was generally believed that animals could not learn without doing things. There was a professor here, Dick Held. Did you know him? Dick Held did a lot of wonderful experiments. For example, he would take a kitten, and he would take the kitten all around the lab and show it where the food was. And then he'd bring the cat back, and the cat would never go to where the food was. However, if you let the cat explore the place and it found the food, you bring it back, then next time it will go right to that place. And it became a doctrine in cognitive psychology that people could not learn unless it involved sensory motor activities. Well, Jose found a cerebral palsy patient imprisoned in a hospital because this kid could hardly move anything and had never done anything. And the nursing staff, tell me if I'm wrong about any of this, the nursing staff considered him to be completely retarded and hopeless. And Jose hooked him up. He could move his head. So, what? Oh, thumb. I thought it was the head stick. Right, and gave him a keyboard. And he very quickly learned to, I don't know how quickly, but learned to make the logo turtle move around. But then he did something that the psychologist thought was impossible, namely, if you want the turtle to move to the left, you type the right character and it turns left. So if I wanted the turtle to go here, I would tell it to turn left. But if the turtle was here, then you have to tell the turtle to turn right. And it was predicted that because he had never had this kind of experience, he wouldn't be able to do this abstraction. And, but he did it very quickly. And somehow Jose concluded that, for example, he couldn't talk, but Jose found by carefully interpreting the noises he made that he did know English, even though he had never shown the ability. And after a few years, he was 3 or 4 years? 5? Yes. And then this gentleman essentially got him to get skillful enough that he got admitted, I think, to Amherst? UMass. Graduated and got a job as a registrar at BU. And all this was impossible according to general principles of the time. So one of the advisors on his PhD committee said, "That's remarkable, but maybe it was just an accident, and this person wouldn't approve the thesis unless he had demonstrated on a statistically significant bunch of subjects, like 5 or 10, which would have taken 50 years. And Papert and I somehow managed to replace enough members of the committee. It's a great story. Then he went back to Brazil and did a lot of stuff involving rehabilitating people and other things I don't know about. But it's a great story. So humans can learn by watching. And 25 years ago, a lot of psychologists would say, no, they can't. They have to use their body and do sensory motor things. It was very strange how deeply rooted this belief was. Do you want to give a lecture? Well, I remember your work, and I remember especially the problem of changing the faculty committee, because here was this great thesis, and its committee didn't like it. There was a mechanical engineer who said it wasn't science. I never figured out what was bothering him, but we managed to get him to resign. This is not typical, I should say. I don't want you to get a bad impression of the academic establishment. Nothing like that ever happened to me in 40 years of teaching, except that one.
One of the most clever things about being a graduate student is to select your committee.
Yes. My daughter, Margaret, did a thesis which involved experimental psychology, and she made the mistake of getting the best professor in haptics to be on her committee. And so instead of a few experiments showing that her theory was right, she had to do a year and a half of running these experiments on many, many subjects. And that's good science. But when you're right, and obviously right, it's a waste of time. The person who gets the theory should get credit for it right away and encourage other people who are not so original to replicate it. So, but she wasn't my student. In fact, I was lucky because, in fact, my daughter was in the same department at the Media Lab as I was. And that would have been considered bad, except that she was there first. because she had grown up in the logo as a little kid. Yeah.
I've heard a little bit about the work of Eric Mueller, who's doing work also with common sense, but also from the angle of event calculus.
Yes, and he...
What your thoughts about this are, how this can relate?
In fact, he's inspiring, and his project is in many ways more developed than ours. He's not working on it recently, but Eric Mueller's Daydreamer was his PhD thesis, which studied common sense thinking in a very non-logical way, and then what's his common sense thing called? Thought treasure. That's probably the most advanced multi-level problem solver that there is, but it only works in the blocks world of simple geometric things. But it's very important, probably. And he spends his time as a well-paid consultant for IBM on all sorts of irrelevant things. And if I got a lot of money, I would liberate him to work on this. So Eric Mueller is one of the best thinkers about common sense. I only know of 5 or 6 other people who have really thought about this problem much. It's quite remarkable that so few people have. Douglas Leonard has done a lot of thinking about common sense reasoning, and he's also produced this psych project, which has a huge amount of common sense knowledge, but the two things haven't gone together. So psych does not have a system to do common sense reasoning with the knowledge it has. And here we have a almost equally big knowledge base of that called Open Mind that has collected all sorts of common sense fragments of knowledge from the web, from people, not from the web, but from thousands of people who like the project and type stuff in. And we don't have a powerful common sense reasoning system to use it, although we're making progress on it. And I don't know if there's any other, is there a third? Do you know if there's any other big common sense knowledge base? Someone said that WordNet has a substantial amount of such stuff, but I haven't looked at it.
Yeah, it's mostly a taxonomy of words.
We conducted an experiment about 2 nights ago. And yes, apparently WordNet does have a significant amount of common sense when measured against Open Mind. We had alignment levels of like 40%.
Really?
Yeah, for things that you could actually compare.
It's interesting.
Yeah, we're submitting a paper next week.
That project was organized by a psychologist named George Miller, who, when I was an undergraduate, adopted me, liked my ideas about learning machines and so forth, and got me the money to build that first neural net machine. And in exchange, I explained what was wrong with the McCulloch-Pitts paper on neural nets, because I was a better mathematician than him, but I had miraculously good luck as a young student of running into just the right people. It was very lucky. I haven't seen much of George Miller since, and he didn't do much. He's the person who produced the revolutionary paper called The Magical Number 7 ± 2, which unified a whole lot of facts about everyday psychology. And then my impression is he went into some kind of not getting anything done state for about 20 years and suddenly snapped out of it and created WordNet and stuff like that. It's a nice story. Again, I wish I knew more about it. That's why he's on the front page of list of people that I was influenced by in the emotion machine. Yeah.
Louis Van Ant's database,
What?
I think Louis Van Ant is also working on building concepts.
I haven't heard of that, but he's an inspiring inventor, Louis Van An, who we tried to get to be a professor here, but what job did he take? Do you know? Yes, he's full of ideas. I don't know if he has powerful ideas about common sense, but if he doesn't, he probably will. He invented those CAPTCHAs, the things that everyone uses to prevent robots from logging into the, these distorted letters and stuff. Someone like Hofstadter, if he were actually a programmer, could probably read the CAPTCHAs, because Douglas Hofstadter, the Gödel-Escher-Bach guy, has some pretty powerful theories of how you could read things in all sorts of distorted fonts, but I don't know if he's tried to break this code. Ray Kurzweil was, I think, the first person to make optical character readers that could read multiple fonts. But it can't read CAPTCHAs. They're too far out.
A lot of people can't read captions either.
Is that right?
Yeah.
Oh, I didn't know that.
Often they get too distorted.
They can ask for another one, though, can't usually?
Yes. Yeah.
Personally hate the case-sensitive CAPTCHAs.
Oh.
Yeah. So.
Oh, because you can't tell what case it is sometimes?
Right. Is that a big C or a little c? It's half hard to tell when it's sort of squiggly and enlarged grotesquely.
Mm-hmm. I guess they could just leave the C's out if they wanted. It'd still be pretty secure. Also could have pictures of movie actors. That would only let a certain class of people to log in. If you have a product that people who like movies are likely to buy, you could make your company more efficient. Yeah.
I think in the lecture that we saw here about Douglas Dennett, he was talking about how he thinks that if you gather enough common sense data, then they'll be able to learn automatically. But real babies start out without any common sense data. They do learn on their own.
Well, are you referring to some particular?
I think they're talking about psych, and they were sharing how many facts they have, and they had this graph, and they said that once they reach a certain point, they hope to be large enough to be able to build upon its own and just expand exponentially.
Well, if you had knowledge about how to do common sense reasoning, then you can imagine a system that would somehow find that knowledge and then be able to do common sense reasoning. But I don't.
What I mean is, if you have the right architecture, you don't need to start with anything. You can start from scratch, and you would still.
I disagree with the point that you're saying babies don't have enough common sense knowledge.
Well, they start with their instincts.
Well,
I mean, psych has enough common sense knowledge. What it doesn't have is knowledge about how to use the knowledge.
And the other thing is that
And I'm not sure you'd call that common sense, because it's not the kind of thing people can articulate, but you'd call it being smart.
one of the ideas is that if you have a lot of knowledge, it facilitates learning, so that you can integrate new information by attaching it to more information that you already know. That's a problem with psych, however, because it actually doesn't get any better at assimilating new knowledge. despite the fact that it's got a lot. So they've noted this, and they're actually changing kind of the focus of it, of the project. They're no longer manually adding predicates by hand, but looking at ways that they can do some sort of like induction to generalize new predicates from the existing predicates.
Because I was considering this statement and thinking about little babies, and then they are born with some instincts and they have their parents around them, but they do start learning facts from the start. I mean, maybe it takes them a few years to start doing it on their own, but they are learning without being just fed directly with facts.
Well, they may be learning all sorts of things internally. Did you read my internal grounding essay? That's the theory that the human baby might have 4 or 5 levels of learning, most of which are not connected to the real world at all, but to little neural structures. So one part of the brain, we may have evolved some little structures that have some group theory-like property, and a big part of your brain might learn how to work that because it's simpler than the outer world. But
if you have the right mechanism, that's more important than to have a collection of knowledge.
yeah, you can't use knowledge till you can reason about it. One problem with psych, which is presumably going to be difficult, I haven't paid as much attention to it as Bo and Dustin have, but I suspect that they're going to have to do 2 things to fix it. And one is that every ordinary statement has exceptions. And does psych have any way to deal with those? But my tip.
Micro theory has to be locally consistent, so.
My typical dialogue is this, you ask, you know that if you see somebody with an umbrella, and you ask a child, well, why did the person get the umbrella? And the child will say, because he thinks it's going to rain. And you say, well, but then what does the umbrella have to do with that? And he says, well, people don't like to get wet. And then you say, well, then why do they take baths or showers or go swimming? And then the child says, that's a good point, I don't know. And I don't think psych doesn't have exceptions. And almost every statement about the world has exceptions. Statements about algebra or group theory don't have exceptions. But that's because you've made the world. It's not very complicated. And the other thing psych probably needs, and it might be able to generate it, is analogies. So you want to say that putting a t-shirt over your head is almost as good as an umbrella if you're not going to be out in the rain very long. And how would it know that? Well, it would have to know something about the dynamics and heaven knows what else to do that. And you might want to, every time you find an analogy, you might want to give it a prominent place in your database, and I don't think psych has any way to do that because it's got an ontology. I don't know. But if you have a hierarchy, then it's hard to make a semantic network or something with crosslinks. And it was designed from the start without that, so do you know if they have some way to fix it? So there's 20 years of work based on some assumptions that are right and some that are wrong. But I don't see why you couldn't get 1,000 people out on the web to go over the psych database and add exceptions to it and add similarity links. So once you've got a big database, I presume you can fix it if the proprietors understand that it needs fixing. I hate predicate calculus.
What is a better language to program psych in?
English. The comments, have you read the comments in psych?
They do have some natural language kind of added in there.
Well, there's this big thing I forget what it's called. I think it's comments. And there's a comment on most of the items, and the comment is better than the comment actually says what the thing means in English. When Lennet started Psych, his idea is that you would start with something like an encyclopedia that has a lot of knowledge, and line by line you would convert the statements in the encyclopedia into statements in the database. And then for bad reasons, he eliminated the sources that the statements were obtained from. Now, when there's a sentence in an encyclopedia, it's in a paragraph, and that paragraph contains all sorts of stuff that you need to really understand the sentence. So in the early versions of Psych, there were links to the source English text. And then he flushed that because I think the Lisp machine didn't have enough memory or some wrong reason like that. And also, he didn't want the words in Psych to be the same as the English words, because then people would think he's being pretentious and it really understood those concepts. So he was reluctant to use English words in the early stages and had hyphenated expressions that would tell you more or less what they were. And in retrospect, I think that the ambiguities in English, there are two kinds of ambiguities for a word. One is it may have several completely different meanings because this word came from Anglo-Saxon, it meant this, and it came from Hungarian, which meant that. And so there are lots of words that have two or even three or four completely unrelated sets of meanings, and you don't want to represent those in the database. But if you take a word like take, that has the order of 100 really distinct meanings, which are pretty much analogous because they refer to the same sort of trance frame with different things in it. And those ambiguities in English words are very valuable. That's what those books by Lakoff and others are about, that there's a huge amount of common sense knowledge hidden in many ordinary words, like the future lies ahead of us, as though time were the same as space, and that sort of thing. Whole books about that. And I don't think Psych knows that. And if you express things in English, those ambiguities are valuable because they let you construct analogies. So that's a third thing that, or maybe that's the same as saying it doesn't have similarity links, but eventually I think a database has to have exceptions, similarities, and analogy generators, and panalogies, in other words. And no one's doing that yet. One of you could do it. And then you could get those thousands of people out on the web typing in elaborate panalogies and making something that we could really use.
When you were devising the Model 6, what were some layers that you considered but didn't include?
I don't remember any others, actually. I mean, at each point, there was a layer that would watch what the other one was doing, and naming the top one self-conscious emotions. I had the layer, and I didn't know what it was called. And I think I got that from an article by, oops, I forget. But it's quoted somewhere. And people Aaron Sloman has 4 layers. And his 4th layer is a big mess, and I think it should be split into 3 layers, each of which is less of a mess. But it's annoying how people try to oversimplify things. As you know, I figure that if you're going to make a model of the mind, you should have more boxes than you need, because it can't hurt. I mean, Occam's razor is okay for physics, but even the physicists have in their mind the possibility that there are a few more laws they haven't got yet, and they don't say this is it. There's an article in the Current Science about the missing spin. Namely, they have a good theory of gluons and quarks, and they predict that the spin of an atom is only about half of what it should be, according to that theory. No, the actual spin is twice what the theory predicts. So this is an article about the missing spin. And he says we need another law, much as I hate to admit it. Maybe there's one more force that we need just to account for the missing spin. I'm sure all the other physicists are screaming and saying, no, you just haven't figured out how to derive it right from the old laws. But I think in psychology, there's no harm in having empty boxes in your diagram. Just instead of the compulsion to make the theory as simple as you can. It just doesn't make sense to me. I mean, my theory is pretty simple, just has a lot of boxes, and it's not clear what box to put things in, but who cares? Eventually somebody will get an idea that says, clearly this is self-reflective and not just reflective. And I think processes that use the various self-images described in Chapter 9 have to go there, and in some sense they're above all the other processes. Not meaning that they're necessarily more important or more powerful, but they just need, these self-images talk about ways to think that the lower levels will use. When you're being sociable, then you're not thinking geometrically or mathematically, perhaps. Yeah?
Model layers from perspective and above are very similar. And maybe the mind, what do you think about the option that the mind keeps spawning additional layers as it needs, up and up, and they're all the types of self-reflectors, but there are different hierarchies, or the more self-models you have, you may split it up and just give them resources to manage them, and then create.
Well, that you could certainly do that in a computer program. I think in the brain you're going to have various kinds of recursive processes, and you don't need an anatomical layer for that necessarily. So if a layer feeds back on itself, then an observer might think it's several layers. But my image is that this is actually a sort of hardware thing, and 6 layers looks like it's enough. And I didn't think 5 layers was enough, but I don't.
A lot of sub-layers, and in fact, what you're saying about more layers building up, I think a lot of large-scale skills developed by large assemblies of ways of thinking that you use it when you need it. So.
Yeah, I think you make new representations. I'm not sure that. What?
Collections of skills that. I mean, what I was trying to understand is this issue of why do we become better at solving problems at a larger time scale. So when you're young, we could solve problems for maybe 5 minutes, 10 minutes, but when you become older, you can spend like many years refining. Your high-level goal stays for many years, but you end up refining little things, and solving a very small subproblem might end up using your different layers, but don't affect the whole big structure of your large goal.
Yeah, well, you can. I'm not sure that needs architectural changes. I once worked on knot theory for a few months, and I don't think that involved building a lot of substructures, not really higher level ones. I wonder what people's model of how they spend their time. There must be various models. Most of us waste most of our time. Doesn't bother us much. Some people are always working on the same thing, and some people don't work on anything for very long.
I wonder how much time a cat can spend on solving a problem.
My dog sits there on the couch for several hours a day looking at something and making sure that no one takes it away. It's really pathetic. Then if you get it to go in another room, it turns into a regular dog in about 2 or 3 seconds. So it's got this parasitic state of mind that it can't get out of without help. Eventually it gets out of it when it's hungry enough. Poor thing. I imagine some people would watch football until they die, except that they would get hungry and they have to get out of that state. So I don't think my dog is very different from a sports watcher, except that the thing she's watching doesn't even move. So she's really good at watching. It might be a magazine that's 3 or 4 feet away. You don't know what she's guarding until, if you get close to the magazine, then she jumps up and gets it. But she seems to be focused on one particular thing all afternoon. And retrievers do that. They have a special register for what they're, not retrievers, but what's the kind of dog that is guarding something. You can train a dog to guard something. And unfortunately, this dog has it built in. What are you guarding? Maybe we're each doing that. I wonder if we should take a break. I couldn't sit in a class for 2 hours, come to think of it. Does anyone want some popcorn? Oh, well, there are these brain waves, and nobody really knows what they do, but I suspect, like there's that micropsychosis theory somewhere in the book, which suggests that maybe you go through a cycle of, remember the Poincaré process? You generate possibilities, then you filter them, and then you elaborate on one a little bit, and then you reformulate the problem and do it again. And I suspect that maybe one brain wave, there's one that runs about 4 or 5 per second, and there's one that, what are the main brain waves? Anybody know?
Theta, they think theta is for binding equations together, 40 hertz.
That's 40 hertz. Okay, so that's a fast one. And there's these 4 and 6 ones. So, yeah.
Alpha, beta, delta, theta, I think.
Nothing like Greek letters. And every now and then you see some theory of them. And I suspect that those theories are nutty because neurologists don't have high-level theories of mind. So you could certainly have microcycles for this manic-depressive Poincaré brainstorming idea. And I think you need a cycle for, if you read the Society of Mind, there's this idea that a lot of reasoning is done by linking frames or transframes and moving, paying attention to the, if you're thinking about a situation and it's represented by a frame with slots, then sometimes you're thinking about the agent that's causing the act for a transframe. You're thinking about the agent that causes the action. You're thinking about what is changed by having done the action, or description of where the situation ends up. Now, if you have two transframes, what you want to do is, at least temporarily, make a new transframe that says if I do A and get B, and then do something and get C, I'll make a transframe for the net result, right? The consequence of these two actions is this transframe that skips the middle step. Now, I suspect that almost all reasoning uses chaining operations like that. How do you use two pieces of knowledge? Well, you use this one and that one to say, if they're about actions, to say that this combination will produce this effect, but then you have to think, well, will it really? What are the side effects and so forth? And so if that kind of chaining is very important in reasoning, maybe there's a brain wave for that. And what that brain does is it does some clever thing of looking at what's in this first slot and then opening the last slot and sticking those both into a temporary frame. So that's how you would do A implies B and B implies C, gives you A implies C. So that's a candidate for something that's so important that there might be a hardware provision for activating these little semantic nets that are stuck in the slots of frame and reassembling them temporarily into a smaller frame and skipping the stuff that's irrelevant. So that might happen at 6 cycles per second, or maybe it happens at 40. And by changing the phase of this thing so that it activates different slots, you can draw different conclusions from pairs of frames. So that's what neurologists should be thinking about. And did someone say something about binding?
Yeah, Jack Cohen actually has the best theory that I've seen on how frequencies relate to brainwaves, what this might mean. And basically, what he says is that it relates to the size of the processor. So if you have a processor that's 9 millimeters, it may be oscillating at a few hundred hertz. Whereas if you have a processor that is the size of the entire brain, it'll be operating in a delta wave, which is maybe 9 hertz. So basically, it relates to the size of the processor.
So it'll be turning a whole section on and off, but it takes a while for it to settle down or for it to... How do you change a context? You probably take a large fraction of a second to change the context and database that you're reasoning with. Yeah. But the question is, what happens in each of these cycles? But that's one theory, but this theory that it's for chaining might be another function, and there's no reason you couldn't use the same cycle for several things. Yeah, how long does a critic take to turn off a set of resources? If it's turning off half the brain, well, I don't know. Maybe that can be done very quickly. Whereas maybe it takes a long time to turn off a particular part that's bothering you because you have to localize it. So it could be exactly the opposite, and the slow things are the ones that make important little changes. He could do an experiment. Yeah?
Maybe it's like scripts in the mind, but if there's stuff that you do often where it's important to your survival, you do it very quickly, no matter what size of the brain it affects. But if it's a resource that you have to turn on and off rarely, then it takes longer.
I suppose, although if you take external actions, it takes 150 milliseconds to react to anything. And another reason that I think sports are silly, competitive sports, is that, you know, the fastest runner is only about 0.5% faster than 50 other ones. If you run a 4-minute mile, there are 100 people who can run 4 minutes and 2 seconds. And so I should say, with the exception of, what's his name? The guy who ran the first 4-minute mile. Roger Bannister. He did a lot of physiology and strategy, and because he was a very fast runner, and he figured out how to beat the other guys. There were only 2 other guys who were also almost running 4-minute miles. And Bannister figured out 4 or 5 tricks that he used all at once. One is, if you look back to see how close the other guy is, you lose 1/10 of a second. And so he had to figure out how close the guy behind him was without looking. And he studied the trajectories of the guy's last 20 races. And the important thing is knowing to win this a running race, you know, you have to sprint at the end. If you sprint a little too early, then you run out of steam. There's no third wind. There's what they call a second wind. So you're almost exhausted, but you can still run another 40 or 50 meters by turning on this extra reserve. But if you turn it on 2 seconds too early, then you won't make it. And he figured out exactly when the other guys were most likely to do this, to go into their final sprint from all their previous races. He had a notebook of the stuff, and he did his final sprint about 1 second before the others did. At some risk, because it was a little earlier than he's used to. So, but generally, as far as I can see, some people have a few milliseconds faster reaction time, and they win, and who cares? It's amazing how all the superstitions about these things. Oh well, I'm wasting your time with my prejudices.
I looked up the brain waves.
Yeah.
And the main types are alpha, beta, delta, theta.
And the frequencies are?
The frequencies are delta is 4 hertz and is associated with deep sleep. Theta is between 4 and 8 hertz and is associated with dreaming and lighter sleep. Alpha is between 8 and 12 hertz and is the typical frequency of brain waves. And then beta is frequency above 12 hertz, which is associated with busy thinking and active concentration.
Incidentally, as I recall, one thing that's interesting is when you're thinking hard about something, the brain waves become very irregular and they're hard to spot. So mostly they may be housekeeping things that aren't involved with exactly how you're thinking. Because when somebody's relaxed, then these waves are quite large, and when they're interested in something, they're very noisy and irregular.
Yeah, you can see that in the pictures they have. They have a special name, gamma, for when they can't quite make it out.
You can see the pictures on that?
You can see the pictures, yeah. This is the gamma.
Oh, I think I'll get one. Which one is this?
That's the gamma.
No, which?
Oh, which cell phone?
Yes.
This is a T-Mobile MDA.
Wow. Right. I could put these talks on it and then you wouldn't have to come here. And you could interrupt. Well, it'll be nice to see the next 10 theories of brain waves in the next 10 or 20 years. So these waves are very big, and the first two are big in sleep, but they're still present a little bit in when you're awake.
I think so, yeah.
One problem is that these are the first brain activities discovered because you can pick them up on the scalp without machinery. But they're only a few microvolts, so an EEG requires a lot of shielding and insulation, whereas an electrocardiogram is really big and you can pick it up on, if you buy an analog voltmeter and have big patches, you can see these rather large currents. They're millivolts rather than microvolts. So muscle potentials are order of magnitude bigger than neural potentials. What are the scalp voltages for the things you're looking at? Or yes, I couldn't believe what happened when FETs came out. It's transistors that had an input impedance of 1,000 megohms instead of just a couple of million ohms. All of a sudden you could build a one transistor thing that would detect when somebody came into the room because the electric field changes. But how hard is it to stick very small needles through the skull? Is there an easy way to do that?
It sounds hard.
You'd think that if you could focus a laser down to what?
Shine light through your skull.
Yeah, but you want to put a fiber optic or something in,
Ideally.
or a wire. Well, eventually there'll be volunteers, and it'll be illegal to indulge them.
I know it's been done once or twice with people who are paralyzed. They'll poke very thin gold wires through the skull. And I know there's one case where it's been successful, and this person can move a cursor on the screen and type things.
And is it sort of permanent? They keep it?
Yeah, pretty much.
Well, once you get good at that.
Yep.
Bo is trying to do these things by piping infrared and things and looking for slightly slower changes, but if he succeeds, he can get a lot of information without making holes in your head.
Very low resolution.
You know that.
But higher resolution.
It's one of my advisors.
But it's higher resolution than you can get with EEG, presumably.
It's higher spatial resolution.
Yeah. Well, if you could get 10 bits out, you wouldn't have to type anymore.
You can tell when you're using, left versus centimeter, basically.
Uh-huh.
Different areas of the frontal cortex.
Mm-hmm. I would just like something so I can think the mouse pointer around. And I think I could do it with my toes. Does anybody want to make a shoe mouse? Then you wouldn't have to stop typing. What have you done in that? Did you make mice for some handicapped people?
Kicking and blowing.
Blowing. Oh, so you were still working with completely paralyzed people.
Yeah.
Did any of them get jobs? Do you know what happened? Mike was his name, wasn't it? You know what happened recently?
No, I haven't been in touch with him.
Well, he had this job as registrar, and then one day he found out that he could get a bigger salary if he didn't work. So, this from the government. So here's this tragedy where when you go on Social Security, you're penalized if you can do some work. It's just a really weird collection of legislation that ends up making people less productive. Because I'm sure he said he'd like to work part-time. But
To leave the house.
yeah,
To be able to leave the house.
yeah. That's a terrible end to the story. The world is funny. Well, what's a good question?
There were a few occurrences of a very basic question that might be good to talk about. One of them, which was, how do you know that this is the correct true theory? These specific 6 layers.
Well, any good theory could be chopped into 6 layers, so. Well, another question is, do you want one theory? Because presumably if you have a complicated system, there are different models for different purposes. And I don't know how to answer that. I'm sure a lot of people will want to say, is this the right theory? But I don't see how it can be wrong. It doesn't make any sense to use Occam's razor until you have two pretty different theories. So I don't know a good, maybe someone like Eric Mueller has another theory. Aaron Sloman's theory is so similar to this one that he has the top layer is very wide sideways, and it has all sorts of bookkeeping and management stuff. And I'm sure if you prodded him, he could divide it into layers and say, well, I don't like so many layers.
I was thinking of relating it in terms of modeling and the process of science. I was thinking of like Bohr's model of the atom, for example, which we know is incorrect in a lot of cases.
Which model?
Bohr's model of the atom.
Bohr, yes.
So if you wanted to find the weight of an electron, for example, you'd need to assume this incorrect model in order to say that there even is an electron. It seems like more of a tool for thought rather than a declaration of what is true as kind of like a belief system.
Well, what's really true is a functional diagram of what all those parts of the brain do. And every simplification would be good for some purposes and bad for others. Another thing is to compare it to other theories. And if you look at theories of emotions, there are a lot of these two-dimensional things which have X and Y, and there are these 4 basic emotions, and then there are 4 secondary ones which are mixtures of these, and those things look very stupid to me, even though people like to collect evidence. So I think you can only compare this 6-layer theory with some other one like Aaron Sloman's, and the trouble is we communicated so much that they're almost the same anyway. Yeah.
Well, I wanted to say a couple of things. One was earlier book, and maybe it was the introduction, or maybe it was somewhere in the middle, where you talked about, you know, how you didn't claim that it was like B theory, but just something that should be considered as food to thought, for thought. I thought you said that in the introduction.
I suppose.
But one thing that
Nancy knows more about what's in the book than I do, probably because she proofread it a lot. Sorry.
But I was thinking too about like Freud. Did he ever actually support his theories? I mean, how do you prove a theory of psychology? And it seems that there are some sort of facets of psychology that don't really get proven. Okay, Skinner had his thing, he proved his. Piaget did his experiments, but did Freud ever really prove it? Or
Well,
also, even Howard Gardner, I was reading recently, I'm not sure that his theory of multiple intelligence is really, I mean, I think he himself is also very humble about it. That, you know,
well, these are simple, everybody in this business, I think, realizes that they're making simple descriptions of some very complicated thing. So the idea, is it true or not, that's a sort of all or none idea that's not appropriate. Now, to me, Freud is very much like Piaget, because Piaget developed almost all his ideas from watching 3 children for several years. And then when he grew up, he was a botanist at first. Then, as his theories became popular, he got in a position to have a laboratory, and he hired people to do similar experiments on hundreds of children. Seymour Papert was director of that lab for a while, incidentally, for 5 years. And most of Piaget's observations from the 3 children were confirmed by these experiments, and some were modified a little, but mostly it turned out to be right. His interpretation of how the children thought about things was more or less true. And today there are a lot of people who argue that children get conservation a little earlier than Piaget said, but these are really very minor things. Piaget talks about when children can count, and some people have observed that some infants can distinguish between 2 or 3 things very early, but as though this refutes Piaget. But they don't consider the possibility that the infant is using a different system, doing it in a different way, which is discarded during the subsequent years. So there's some data on when children recognize faces. And I'm convinced that very young infants recognize faces in a certain way, and which they don't use later. And so this is a stopgap that's used for improving attachment of the infant to the mother, or mother to the infant, rather. And it's a little prop that goes away, and it's many months later that the child actually recognizes facial features in more or less the way the adults do. And it's still not known much about how that works. So Freud, as far as I can see, except for a few controversial things like the role of sex in infants, I think he was onto some theory of attachment, but didn't formulate it very well. But all the phenomena he observes are like repression and sublimation and people not knowing what their real motives are. That's as solid as anything, and he doesn't, because he's before computer science, as Piaget was, he doesn't have procedural representations of how these things work, but because he was stuck in the past, so to speak. Can you imagine trying to do psychology before computer science? As far as I can tell, Aristotle was as good at psychology as as people like Freud, things didn't really change till people like George Miller in the 1950s and 60s started to introduce more procedural concepts. Oh. I think somewhere in the book I quoted that statement by Searle, who was saying, when I was younger, people likened the brain to a telephone switchboard or something or other, and today the latest fad is likening it to a computer, and he's suggesting that this is just the local fad, and I don't think so. I think the computer, the idea of procedures that can edit themselves and things is here for good. It's not a fad. Well, what I want to know is how come speakers got so good? Because 3 or 4 years ago, cell phones only made little treble beeps, and now they seem to produce all the way down to, what is it, about 150 or 200 hertz. What's the trick? Anybody know why? Why is a half-inch size speaker so much better than it used to be?
I think some things have gone from piezo speakers to electromagnetic in recent years.
You think they've gone backwards?
The coils enough that,
So it actually moves a lot.
yeah.
When you get right down to it, the human throat has an aperture that's only this big. But I never expected to hear hi-fi from a half-inch speaker.
I was just thinking about what was mentioning that how semantic networks or frames might represent the brain. I'm just thinking, since we are able to visualize how a frame might occur in a 2D space, or how a semantic network might be represented in a 2D space,
In what space?
in a two-dimensional space, is it possible that higher level areas are utilizing some of the lower level visual areas to do something, to do the calculations, if you will? Or
I forget. Are the higher vision levels used by blind people? I think I read somewhere that they are, but I can't remember if.
no, I'm not saying the higher visual level, higher visual areas using lower visual areas. I'm saying higher thinking areas using high level visual areas.
Well, what if you're blind?
Oh, that doesn't matter because representations and we will still work.
Yeah. Well, I was just wondering if.
Braille is represented in the visual area for blind people, I'm pretty sure.
Wow.
Yeah,
Don't quote me on that.
there's an interesting study on that. Basically, disrupt the activity in the visual cortex. And a blind person basically is just as good as a sighted person for reading Braille. But if you take a sighted person and sort of blind them for a week, they actually get to be as good at, pretty much as good as Braille as a blind person. But actually introducing visual data through the eyes will sort of push or elbow out the capacity to process Braille.
So you could learn faster, or.
I don't know if it's faster, but I think the implication was that the visual cortex does some sort of data management that makes processing Braille easier. And it's really only available if your eyes aren't shouting at it.
I remember reading.
So it,
Oh, sorry.
go ahead.
I remember reading that the visual in blind people, that the visual cortex will be used for hearing and for other senses too.
For hearing also?
I thought it was for hearing. It was either for hearing or touch.
That's one of the explanations for why there are so many, disproportionately many blind musicians.
Is it disproportionate?
It is, yeah.
Making copies of
Also, it could be because the job is available.
Yeah, that's the alternate explanation.
Good.
This kind of reminds me of the tricks people are starting to use now in high performance computing to make the graphics card do number crunching instead of just play graphics.
I can think chords, and I can't think of them if my hands are closed. So it's really peculiar. The sound goes away in my mind because I grew up with a keyboard.
A friend of mine is a mathematician, and he says he thinks in R2. So he can manipulate things visually. That's kind of how he solves equations.
R2, you mean?
In
a plane?
A two-dimensional plane, which he uses his visual area to kind of do symbol manipulation. I imagine he could do it with his eyes closed.
I knew a woman who could remember all sorts of things, and I asked her what some date was, and I asked her what she was doing sometime in the future, and it turned out that she kept a calendar here in her visual field, and she had a little notebook here, and she had some other stuff, and she could write stuff into the calendar or the notepad, and it would stay there. And so I asked how she got it, and she said she'd always had it as far back as she could remember.
Just for the future, or was it her history as well?
No, it was, the calendar is about the current month or so, but she can stick in it and then it's there all month. I forgot to ask her if she can remember last month, but she said that she was surprised when she found that other people didn't have this. There's an article by Francis Galton, who's a great psychologist of the 19th century. I think I mentioned this if you look on my webpage, there's something called Introduction to Logo Works, which is a cute article about some aspects of children's thinking. And Galton was, in many ways, he was the first good experimental psychologist. He wrote a book in about 1880 called Inquiry into Human Faculty. And in this book, there's a chapter about how people think about numbers. And what he says is that about 30% of people, presumably in England in the 19th century, have places in their visual field for numbers, and they're very definite. Like a child might have 1 here and 2 here and 3 here and 4 here, and there's no particular thing in common about where these numbers are. But then, for a lot of those people, they then have 5, 6, 7, 8, 9 in a row somewhere. And he thinks that that's because I forget, I read the paper, but I've forgotten, but obvious conjecture is that they learned these first numbers painfully. Did you know that 2-year-olds only go up to 2, and 3-year-olds only count to 3, generally? And 4-year-olds count to 4 and then quickly go up to 10 or more. And that's very strange that you can't get a 2-year-old to count to 4 very well. Yeah?
I thought it was really interesting what you were saying before about the about how infants are said to recognize numbers of things, and I've read about those studies, how, they'll see like two items flashed on a screen, and then they'll see three. And then you mentioned that maybe it's that they have that opportunity to know that when they're infants, and then they forget it. And just today I was reading about a study and I think it's unreplicated at this point, but that showed that that infants up until, I think it's, before 9 months, that they're able to distinguish not only human faces, but also monkey faces, and that by around 9 months they lose the ability to, and they can only distinguish faces within their own species.
Wow.
And it makes you wonder whether that number recognition, that ability to kind of, when infants gaze longer at two items or two dots on a screen than they would at one dot on a screen or three dots, when they sense that change, whether it's just pattern recognition that they're sensing, and that...
Oh, good, yeah. In fact, I had a conjecture in that Logo Works paper that there's only a few patterns that three objects can make. That is, it forms a sort of triangle, and it could be a long, thin one, or they could be about equal, or it could be like in a line, only with a very big angle. So you could recognize threeness just by recognizing 5 or 6 patterns, whereas with 4 things, there might be 20 or so much more different patterns. And so it could be that around the age of 3, you have to give up. I'm sure you still keep them, but then you have to start representing numbers in another, better way. And everybody in this room can count. If I have a picture, you can look at it for a while and say there's 15 points there. And I suspect that when I do that, I have an imaginary line that starts up here, and it goes bleep, 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 bleep. In other words, I'm not using a pattern, but I'm using a sequential process that in my case involves making this imaginary line, because that keeps me from counting things twice. There are probably people who will miscount 10 things because they don't have such an orderly way, and they have to remember which ones they've counted so far. And by the time there's 15 points, you're liable to forget. Anyway, Galton observes this about, and he calls these number forms. And I thought that maybe this is very important because then there's the 70% of people. How many of you have a number form? How many of you think of 1 as being sort of up and to the left rather than? No one here? Well, many adults forget it because a larger fraction of children that I've asked have them. But I had a friend who remembered how he got it. He's a professor of mathematics at Harvard, and he sees numbers as quite a lot of them as having definite places, and they're in different colors. And he said, by the way, I remember how I got them. I used to, when I was very young, I used to lean out the window and think about numbers, and I'd sort of imagine them on a little hill across the yard, and that stuck with me. Anyway, so these things would happen by little mental accidents. But the interesting thing is that since this is not part of modern psychology, and so it might be that there's differences between those people who have these visual representations and others who don't. And it might be that you should adapt how you teach arithmetic if you must teach arithmetic. And having a uniform way of teaching doesn't make sense if there are 3 or 4 kinds of people in your class who think about these things in different ways. So that's a big educational problem. I mean, all teachers probably know that some children learn much more from verbal descriptions than diagrams. And maybe some teachers don't know that, but that means that you might want to change the educational environment a little bit for people who are more visual or more auditory or more both or whatever. In these days, it's hard to ask teachers to do anything because they have their hands full with those standard test problems. Does Brazil have them?
Not yet.
It has to be, it's pretty dangerous.
I remember one experiment that I did while I was in Geneva on numbers, and the task was very simple. It was to ask children to construct the same amount of, blocks or pebbles somewhere else, and they could look at the series. So
They could look at the other one?
No, they looked at a certain arrangement.
Oh, yeah.
And in some situations, the arrangement was regular. So it was 3 rows of 4. And in the other one, it was just marbles that were like messy. So you ask them to look at it, they can do whatever they want, they can take notes and so on. And then you cover it and you ask them to reconstruct the same amount elsewhere. And this was about 4-year-olds. And what was interesting is when the collection was regular, what you get is this combination between gestural and visual with very small numbers. They never counted the whole amount because that was like too high numbers. So they would say things like, and there are 3, and there are 3, and there are 3, and there are 3. And then they would reconstruct using this heuristic. But what was interesting is that when the collection was not regular, when it was messy, the singing came in and it became more important.
Singing?
Singing. So they would not just do the gesture, but they would say, and there is 1, and there is 2, and there is 3, and there is 5, or what? No, not 5. 5 was too big a number. Mm-hmm. And many of the children would do that.
Wow.
So what was interesting here is that they found all these ways of building these clusters that were small numbers, inventing the glue to bring them together, and using the different modalities that they had available to actually create this template that then they would use to reproduce the same number.
That's very funny. I guess we grown-ups find it very hard to imagine when counting 4 things was a big job and you needed to make a special representation for it.
And when you asked at the end, how many are they had a really hard time because as you explained when you were inventing this rule for 15, the hard thing is to not count one thing twice and get all muddled up. So
right.
the children I was working with, they knew how to count. 1, 2, 3, 4, 5, 6, 7, 8, and you ask them how much can you count? They say 100, but they cannot really keep the cardinal. They get messed up. They don't have good strategy of putting aside what they have counted. But anyway, what was worthwhile for this conversation is this use of rhythm also, not just oral patterns, as a way of mnemonic technique almost.
Well, in that paper on music, which is on my homepage, I had about 10 theories of what people use music for, and I hadn't thought of that one. So if you have a rhythmic structure, then you can put more arbitrary things in it than you could without this temporal division. Yes, it's a great mystery why people like music. And in that paper, I have the theory that popular music is used to stop you from thinking various kinds of thoughts, whereas classical music encourages you to think about. What?
He said it's a nice dichotomy.
Yes. I don't know if I put it that simply. I think I concealed it.
Where does jazz fall in that?
I don't like it much, but I don't have a good theory of why. Well, older jazz has this repetitive chord structure, which, well, what do you call this 12-bar thing? Is that blues? That's incredibly boring for me.
The guitar parts are very interesting sometimes.
Yes, I suppose. You mean the rhythm section also, or?
Well, no, the drums and bass are very straightforward.
Yeah, you don't want to distract people by, although every 8 bars or so, the rhythm section does one little thing and then you get interested again. Very small variations. But breaking it into temporal blocks is sort of skeleton for making larger structures. If you didn't have measures, I don't understand ragas. They have 14 beats per measure, and I'm completely incapable of counting that without counting it. So anyway, I think it's 9:01. Did the popcorn get eaten?